Hello, everyone. Welcome to Coffee with Caleffi. Today, we're talking about radiant design and how it overlaps with system balancing. So, this is one of my favorite topics. Saeed Danesh is our presenter. He's from REHAU. I worked with him for about 5 years when I was at REHAU. So, the two of us have covered this topic a bunch of different ways with a lot of different audiences, and we've kind of picked the greatest slides that we can find out of basically a 2-hour presentation to put together here. So, a couple FAQs before we get started. If you're having issues with the audio, probably log back out and log back in. That's usually the best way to fix it. If you want to copy the presentation, hit yes in the post-webinar survey, and that'll put you on the list that will send you a PDF. And then we'll also throw this on YouTube, and you can go back through all the years. We're actually going to have our 200th Coffee with Caleffi next year. So we've been doing this for a while, and we've got all those up on YouTube. If you have a use for a certificate of attendance, we will email that to you after the presentation as well. And then just check with your authority having jurisdiction if that complies with their requirements. We were talking about this just before. We're going to build this in a template that we list, all the important information, learning objectives, the presenter, time and date, and things like that. So it should comply in a lot of different places if they accept a certificate of attendance. And then Hydronic 35 is out now, so this is available always on the website. I'll put that in the chat as soon as we get rolling here. And then you can also sign up to get a hard copy mailed to your house or to your office. Then I wanted to mention we try and do a spotlight each month. So Women in HVACR has a new scholarship, a new amount of scholarships that are open. So the $5,000 scholarship, they've got a total of 6 of these. You can use this for a bunch of different education opportunities, technical college, trade school, 4-year degrees, all that type of education that's industry related. Applications due by June 1st, and I'll put that link in the chat as well as soon as we start. That has more of the details about what you need to do to qualify. Next month, we have one of our directors at Caleffi, Kevin Freet. He's going to be pulling a bunch of questions about domestic hot water recirculation, really from the tech support lines and a lot of engineering conversations we get into about how to get a DHW system back to intent or to decide what type of valve would be the best way to accomplish the task. So that'll be a good one. That's kind of one of our most requested lunch and learns outside of Coffee with Caleffi as well. And then today, we have Saeed Danesh. So he's a technical project specialist at REHAU. He has a master's in energy engineering. He's working with he's very active with the different industry groups with ASHRAE technical committees and things like that. He's one of my favorite trainers to work with. I'm going to turn it over to Saeed. He's going to toggle his camera on, and then we'll go through the slides and we'll keep an eye out for questions. So if you have anything that you want to add or anything that you're unclear about, go ahead and type that into the chat as we're going. And we'll get back to everybody after the webinar if we don't catch it while we're going through the presentation. And yeah, I think that's all that I have. So take it away, Saeed.
Hey, Max. You can see me and I'm good,
Yep,
the audio and video.
looks good.
Awesome, man. Thanks for having me, Max. And yeah, as Max mentioned, my name is Saeed Danesh. I used to work with Max, very proud of those times and always happy to work with him. I work in sales office Vancouver, British Columbia, and I cover 4 Western Canadian provinces. But now I'm in Reno, beautiful Nevada. We are doing a skill builder as a part of REHAU. For those who don't know this, it's one of the highest level of hydronic trainings in the industry. So if you are interested in any of the hydronic topics for a full 2 days training, please reach out to your REHAU contact in your region or your rep. We'll make sure you get to one of these trainings, and definitely you're going to enjoy. So a bit about REHAU, our company. It's a polymer manufacturing company, the highest level, with over 20,000 employees in 150 locations. We are international, German-based, still family-owned business. We work in many, let's say, sides of the industry, like aerospace, we work with Boeing and Airbus. And like furniture, we work with IKEA and Herman Miller. Appliances like Maytag and Whirlpool. Also, we are very active on the automotive side. We are the tier one manufacturer for Mercedes-Benz bumper and other cars like Volkswagen and Audi and BMW. But in the construction side, where I work for, we have some products like windows and doors, UPVC, but mainly we manufacture the highest grade of PEX, which is PEX A, and the accessories, which is good for radiant heating, radiant cooling, snow and ice melting, geothermal application, and also plumbing and water services. In REHAU, we are driven by the engineers. We value innovation, and also we value the education and sharing the knowledge topic. So feel free to reach out. Feel free to add me on LinkedIn. I'll be more than happy to get connected with you guys and talk more about the topics that you guys would be interested in. But specifically today, we're going to talk about radiant systems and the balancing. What is radiant technology? In the HVAC world, any system that provides more than 50% of the heat transfer to the room and the occupants through shortwave radiation, we can define it as a radiant technology. And in our world, it's normally a network of a pipe, which is either embedded in the floor, wall, or the ceiling. Based on my experience, last 12 years, over 90% of the systems that we work with is the floor radiant systems, or mostly radiant heating, or it could be radiant cooling as well. The concept of radiant heating is we are sending warm water through a network of the pipe, which is mostly, again, embedded in the floor. And there is a conduction heat transfer where the floor gets warm. So this is very important. We are talking about the low temp system. When it comes to the design consideration section, we're going to talk about it, but the advantage of this system is, like, we are talking about 100 to 120 degrees max supply water temperature. So this considers as a low temp and very efficient system. By warming up that floor surface temperature to the point that it starts radiating towards the objects in the room, towards the surfaces in the room, based on Stefan Boltzmann theory that any warmer objects tend to, radiate towards the colder surfaces. That's the fact that we take advantage of. Of course, some natural convection happens at the floor level. I would say about the 20 to 30%, but the majority of heat transfer to the other components in the room or even occupants are happening through the shortwave radiation. On the left photo, you can see a operating radiant system. The photo was taken with an infrared camera. It's very nice. It shows different points in the room. And again, the magic of radiant system, you can see all of those points, they are within the same ranges of temperature. So another great advantage of radiant application, you experience minimal thermal fluctuation. The types of these radiant systems, we mostly see like embedded surface system, or ESS, where it's a unidirectional type of a heat transfer. On one side of the slab, it's mostly insulated, so the heat transfer happens on only one side of it. And this is, again, more than 90% of what we see in the industry. We also have thermally activated building services or systems, aka tabs system. These are bidirectional, so you will see the heat transfer on the either side of the slab. The slab is exposed, so it will act as floor system in one level, and it will act as a ceiling system in another level. We have some project samples on this on our website if you want to go and check it in REHAU North America. Very, very successful project. It's a little bit complicated in the design side, but we can definitely help with that. Also, we have the high performance ceiling panels. These are the panels that it's made from metal, and you have your tubing attached from the backside. Very common in Europe. It's on the baby steps in North American market. But again, since it's out of our scope, we're gonna be focused on the first systems, that is ESS. So what are these ESS systems? It could be the structural slab, also known as a wet system, because you're pouring concrete or gypcrete. And the structural ones are either on grade or below grade, like a basement level, or it could be suspended slab, like the photo you can see here on the left. It's over a metal deck. This is where the contractors come and pour concrete, normally anywhere from 3 inch to 6, 7 inch, and we want to see at least 2 inches of concrete coverage in these systems over tubing to keep the integrity of the thermal mass. So for a structural slab, 2 inch above tubing is your magic number. Also, we have another wet system. This is also for a new build, which is called overpour system. This is normally for like 4-story walk-ups or wood frame buildings, where you staple down your tubing over your plywood subfloor, and then you come and pour 1.5 inch layer of concrete or gypcrete. In these cases, since these systems are not non-structural, all you need is only 3/4 of an inch of gypcrete or concrete coverage above your tubing system. Also, we have dry systems or panel systems. These are perfect for retrofit application. In the photo, you can see our RAW panel and RAW board system, a great application developed by a REHAU engineering team. The photo on the right has the highest, let's say, BTU output of any other panel system in the market. If you do 6 inches on center, you can get almost 30 BTUs per square foot using only 110 degrees supply water temperature. This system can also be installed on the wall if by any reason you are short in the floor space. Like for example, in some bathrooms, if they have like multiple exterior walls and you're short in the area because you have your bathtub and toilet and everything, you can use a portion of a wall using one of these radiant panels to provide more heat to the space. So let me ask a question from all the audience here before we go to the design. Has anyone in this room designed or installed this system before? I think Max can have the access to the answers.
Yep, so I've got the poll launched. We're starting to get some responses there, so I'll give everybody a second to put in their vote. And one of the things that I wanted to mention, we in the pre-submitted questions, we got a bunch of questions about radiant cooling. So that is another topic. I'm going to put a link in the chat as well for a webinar we've done about that, and we're happy to follow up about that. A lot of similarities, and then there are some things that are different as far as the flow rates and the delta T's and things like that. So we won't cover an in-depth radiant cooling presentation today, but we do have one that I'll send a link to, and that's also a great follow-up that Saeed and his team can really get into the details for. Like, yeah, this sounds like a great application for it. A big glass atrium in a new construction
Oh,
building or something like
definitely.
that are always a good fit. So
Yeah,
yeah,
and
so
then
now go ahead.
I, we could, have another session maybe in future if we get, lots of interest in the topic. I would be more than happy to go in depth with you on the topic of radiant cooling.
Yeah, we're probably due because the I was just looking and it was 4 years ago that we covered it last, but we get questions about
Mm,
radiant cooling all the time in the pre-submitted questions, even if it's like we talked about before, a plumbing webinar or something like that. So
all right.
okay, it looks like the responses have leveled off here. So I got a 66% yes. So 2/3 are saying that they have. So I'm gonna turn this back over to you.
Right on. Yeah. So we're gonna go through the process overview for those who dealt with this system before. Um, Normally, we are trying to address the project need. First of all, the local jurisdiction, we want to follow the codes. And then if you're dealing with commercial project, we're gonna make sure the engineers are happy with the design, and also the people who are dealing with the design as the end users and the occupants. So you got to consider all of this besides the energy efficiency consideration, lower initial cost, and also the most important topic within the radiant world, which is the thermal comfort. So we have a great engineering team the designers who dealt with these systems for so long time, and we would be more than happy to help with that. And that's actually a hydronic designer job, to make sure you select the right system, sometimes by even upsizing a bit on the plastic pipe and saving a lot on your costly part of the system. So we would be more than happy to help you with those. These steps that I'm going to talk about, we have a software for it. It's called LoopCAD. It's developed by a Canadian company called Avenir. It's a very, very nice application which does radiant heating, radiant cooling, and snow melt. And it has these formulas built into it. But I want to just explain to you the fundamentals so you know what's happening. But if you wanted to talk about the app, if there is anyone in the room that dealt with this app before and has questions, I would be more than happy. Or if someone prefers, doing a manual calculation, always, that would be fun too. So these are the steps. First of all, you need to do the heat loss of the space. If it's a commercial project, you may, and in most cases, get the number from the engineer. That mechanical consultant team works on these numbers, and they go and size their heat source, which could be, electric boiler or gas-fired boiler or a modcon boiler or any type of a, heat source. That's the basis on, the heat loss calculation. And then on the radiant panel side of it, where you have it in the room, you want to define the unit heat load, which is technically the usable area. And also then we going to go calculate the floor temperature, the pipe size, the spacing. We have some best practice that I'm going to go through it. And then by knowing the water temperature and the flow rates, also the head losses, then it takes us to the final steps, which is sizing the circulator and sizing the expansion tank and other components of the mechanical room. But these formulas, you can see in the next slide that these are the main three formulas that I'm going to talk about. The first one is the required floor temperature, which equals the radiant output, let's say unit output, divided by heat transfer coefficient plus indoor design set point. So indoor design set point, normally for radiant system, I'm going to talk about it based on ASHRAE 55. It's somewhere between 68 degrees Fahrenheit to 72 degrees Fahrenheit. In some areas, we may get the questions from the mechanical engineers or some owners that, oh, I want higher numbers. We're going to talk about it. This is a different system than a forced air. You don't want that higher indoor design set point because your surfaces are warmer. So that's based on the various researches that ASHRAE and other organizations like CBE did. They figured out 68 to 72 would be a good number. Also, the heat transfer coefficient kind of plays a very important role, because in the heating mode, because you're taking the advantage of the natural heat transfer through the convection, you have a higher number. And it's the totally opposite way for the cooling. But for when you have radiant heating system in the floor, your heating transfer coefficient is somewhere around 2, as opposed to, if it's in the ceiling and the heating mode. I'm going to bring up an example. Let's imagine we have a 1,000 square foot project, and we calculated the heat loss as 30,000 BTU per hour. So if you divide this by that number, it gives you 30 BTUs per hour per square foot, which is your unit load. And if you divide this by almost 2 as your heat transfer coefficient and add it to 70 degrees indoor design set point, it gives you the floor temperature. If you get to the temperature of 85 at floor, it means you can compensate that heat loss. So what's next? What water temperature we need to bring the floor to that temperature, 85? And that's calculated through this formula, which is a factor of total R value above the tubing, like the concrete and floor covering, also the pipe spacing. And in, let's say, again, a rule of thumb would be somewhere between 1 to 1.5. And also then you add it to the floor temperature. In our example, if we want to consider something in between, you have 30 BTUs per hour square foot, you multiply it by 1.3 and you add it to floor temperature of 85, you'll need somewhere between 124 degrees or 125 degrees supply water temperature to make sure you're getting to that 85 degrees floor temperature and then compensate the whole heat loss of the space. And last but not the least of the main formulas, this is the very famous hydronic formula to calculate the flow rate. And you just divide the BTU per hour, or your heat load, by fluid density times 60, just to convert the hour, and then a specific heat of the fluid, which, for the water, you can kind of round up the denominator to 500 times, the fluid density, and again times by delta T. I'm going to talk about this. The regular delta T in hydronic industry, especially radiant, is 20 degrees. So in order again to make it a little bit easy to understand, I rounded up the whole denominator to 10,000. So your magic number is whatever BTU you have for your building, you just divide it by 10,000 if you're using 100% water. Then you can tell how much GPM you need for the entire building. In our example, where we had 30,000 BTUs, you will need 3 GPM to send to the room to make sure you can address the heat loss. And then it's your next step, where you run your tubing to each room. Radiant systems are very nice and zonable. So manifolds normally come from 1 station to 12 stations. It means you can serve rooms up to 12 rooms at the same time and control it. And keep in mind, using the ProBalance manifolds, REHAU ProBalance manifold, you are able to adjust this loop GPM from 0 to 2. So as an example, you can see in the photo, you have 2 rooms, similar in the, let's say, a square foot, but one has 2 exterior wall. It means it has a higher head loss. So no problem. Even if they have the very similar loop length, you can just adjust it on manifold, and you send 1 GPM to room A and zero 0.5 GPM to room B, and take care of the balancing very easy. Max is going to talk about it more. And then after having the GPM, you can see in this formula, the next step would be calculating your head loss. There are several tools, as I say. LoopCat does it as the first easiest way for our team, the hydronic designers, or you can have the access to online head loss calculator. You just enter your pipe size, and then your flow rate, which we calculated in the previous slide, and the fluid type and the length of the pipe. Then fluid temperature plays a very important role. Then you can see how much pressure drop you're experiencing through your loop. Or also you can refer to online, let's say, graphs or charts, like you see the one on the left photo here. Again, the good thing we have in our manual is, like, we show it in different ranges of temperature, like 60 degrees, 120 degrees, 140 degrees. So you could have a better understanding on how much you are like losing pressure. And once you have the pressure drop and you have the GPM, that's your next step to go and size your pump. Depending to your pump manufacturer, you can always refer to their graphs. You can find that best efficient pump, let's say, point of the pump, which is the, let's say, some side of the curve that your pump will operate at its maximum efficiency, and then pick it very easy. I think this is from, they can find more information on Hydronic 16, right, Max?
Yeah, so this was a journal that we did on circulators. This is back to 2015 is when we published this. So there's a lot more ECM technology from here, but the concepts are the same. You still want to find what that operating point is going to be to select a pump. I would say that it's easier with ECM pumps because you have to be in a range. You're not going to end up at a specific point, and they can operate really efficiently kind of within a larger area, which is helpful, but you still have to do the math. So you still need to find the circulator with kind of the calculations that Saeed described in the last couple slides there. And one really important thing is knowing the percentage of glycol, because that can really affect the whole equation, everything that you're putting into LoopCat. If it turns out that, oh no, it's not water, it's 50% glycol, you may have to relook at a couple different things there, and specifically the pump sizing. So on the next slide, we'll talk a little bit about balancing options. So what we wanted to do here is kind of, I put together this building. I don't want to see a bunch of comments about how this is the worst drawing of a building that you've ever seen. This is a conceptual sketch that I put together. This would not work. I don't have the doors in the right spaces. Nothing's to scale here. But what we wanted to kind of illustrate is, let's say that you're putting together a building and you've got some office spaces on the left here. And then you've got one big warehouse maybe on the right. That's zone 9. So even between offices 1, 2, and 3 on the top there, you're going to have a different amount of BTUs required, just because the 1 is a corner office. Maybe we'll say 4 is a big glass atrium. But then even the uses of the different spaces. So I think that what zone 8 is a yoga room. So that might need to have a completely different temperature consideration than, like, what are we doing in the walk-in freezer? In some cases, radiant is just used to keep the frost from ruining the concrete. So that's a completely different thing than what you'd be doing in a yoga room where people are already like moving around and pretty warm. So we're going to need different flow rates for all of those potentially. So that's going to be one thing that we have to look at. So how would you, this is a question for anybody to write into the chat here, how do you balance this building? We've got 9 zones that are pretty different. Can you use the same balancing valve here, or what's your strategy? So as people are typing in their answers here, Saeed, is this something that comes up quite a bit as you're looking at a project that you
Well,
throw into LoopCAD?
yeah, Max, a lot. Again, depending to the type of the occupancy and the application. As you mentioned, for example, we have a different set point for a room which is used for yoga, or it's for office, and to compare with a warehouse, number 9, zone number 9. But the good thing again is, you are gonna talk about this, but Radiant system is very flexible, and you can, supply with different, let's say, ranges of temperature, and get to different set points in each zone.
Yeah, we've got a couple answers coming in that you can do it with a radiant manifold, which we'll talk about. And then you could
Mm,
also put a different circulator for every single one of these zones. You could size the circulator specifically for zone 1. That would probably be overkill in a lot of cases. Maybe if you had 2 enormous zones like zone 9, it makes sense to just have 2
mhm,
circulators that are properly sized. But I'd say balancing valves are going to be a little bit better way to do that, because all of these flow rates could be zero point 0.2 GPM or something like that. You're not going to find a circulator that's going to be that small anyway. So
exactly.
we'll go to, we've got, yeah, a bunch of manifold answers. So the manifold question, both the Caleffi and REHAU sell a manifold that will do this task to balance by drop, by individual circuit. So let's say for the zones 1 through 8 there, that got kind of small, but those were all of the office zones. We might have completely different lengths of pipe there. We might have different pipe spacing in the yoga room than we would in the office 1. We might be at 12 inches on center, or 6, or whatever, depending on the amount of heat that we need to get into that space to keep a similar supply temperature. We could have a different boiler for every zone. We could have 120-degree set point in one zone, 100, 140 in a different zone. That's not really realistic either. So we want to adjust, and you can do all this in LoopCAD or a Radiant design program. What is the flow rate we need if we're going to supply 120-degree max to these zones? How do we modulate that? So you can take any of those individual drops of the manifold and adjust that. So one of the cool things about doing this with software is it's going to say you're going to need zero point 0.2 GPM here, 0.3 here, 0.1 here, or in some cases in the warehouse that we'll talk about next, it might be 4 GPM for an
Mm,
enormous part of a warehouse or something like that. So all those individual offices, because they're so different, that's a great opportunity to balance at the manifold by individual circuit. So on the next slide, what about the warehouse? Do we need to balance each individual circuit there? If it's a big rectangle and each one of those lengths of PEX is 300 and 4 to 315 feet of pipe to work around a little structural detail here and there or something like that, do we need to balance at each individual drop of the manifold? Probably not. So in that case, if we've got a pretty consistent big area, as long as one of those loops isn't 200 feet or 105 feet or something like that, what we could do is balance by the entire manifold in that case. So what I show here is an automatic balancing valve. So you would select just 4 GPM, a 4 GPM cartridge for that entire group of the manifold. Maybe that's the west side of the big warehouse, zone number 9. And you could balance it that way. So then you have 4 GPM there, and then the lower manifold, you select the same cartridge because the circulator is going to want to go path of least resistance. So it's going to go through the least hydraulically remote manifold first. So if you didn't balance this, you might have a lot more flow through the east than the west or something like that. So that's where the automatic balancing valve, you just select the right cartridge, you put 2 of those in, and then you kind of have balanced east and west in that big warehouse, but don't necessarily need to get into the every single drop of the manifold unless there was one short one, or maybe the case is there was both of the manifolds that we're talking about. Let's say somebody puts a nail through one of those
Mm.
loops, you could isolate it. So that's kind of the advantage of still using a manifold like that, even if you're not doing balancing per drop. And then on the next slide, I'll show a manual balancing valve option here. A disadvantage of a manual balancing valve is that if you adjust one, it affects all of the others. So if you balance that valve, kind of like the individual drops of the manifolds with the circuit balancing, if you take one all the way down to 0, you will see more flow go through the other loops. So that's important to know. This type of manual balancing valve is helpful, especially in an existing system or in new construction, because you can just pull the pin. You don't need a tool, and it's going to tell you what the flow rate is. So you can say, we want 4 GPM here, 4 GPM here. We pull the pin and see that we have 5 and 3. You can balance that out and go back through and verify. So that's another way to use a different balancing technology to make sure you've got the right flow rate through the east and west side of the warehouse there. So no specific balancing recommendation that's going to be one size fits all, but those are a couple different options that can reduce the commissioning task, because you could go through, I'd have to count here, all 24 of those circuits and balance them. That might be overkill in this specific scenario. You might only really need to fine tune the office space there.
Mm.
So, and then I think, oh, there's a little cutaway of the inside of the valve that shows you that. So now
Yeah.
I'll turn it back over to Saeed to go through some other installation considerations here.
Yeah, sure. But before we move, like again, some consideration here are very important, like the supply return strategy or even your manifold location. So coming up with a smart manifold location in project like this can save a lot of, let's say, waste pipe and loops. In a way that, for example, again, as you mentioned, in the office area with multiple, let's say, demands for different type of indoor design set point, you can put a central manifold and control it by each circuit to each of those zones. And then you can put 2 manifolds beside it just to control the zone number 9, and make sure you're controlling it properly by a zone valve, which I'm a big fan of those auto balancing zone valves. So yeah, before we continue with the design consideration, these are some rule of the thumbs and the best practice that I'm gonna mention. Of course, project by project, depending to the owner, let's say, needs, and also mechanical consultants' need, this can vary. But again, I mentioned it in the previous slides that we get a lot of question about the comfort range. Um, these are 2 ways to look at it. First of all, based on ASHRAE 55, which is specifically working on the human comfort in the building, they defined 6 primary factor on this, thermal comfort topic: metabolic rate, clothing insulation, air temperature, which is inside the room, air speed on your skin, and humidity of the air, and also radiant temperature. We talked about this. The radiant temperature is provided through shortwave radiation. That's why having a radiant system in your application can help a lot for you to feel comfortable. And if you want to address these with a radiant system, you want to make sure you follow the ranges that ASHRAE 55 recommends. We also work with CBE in part of my presentation, I mentioned their name. CBE, Center for Built Environment, is a group of PhD students, master students out of University of Berkeley, California, and they are focused on highest level of research and studies on HVAC systems, especially the ones that are dealing with the high performance building and the ones that are addressing human comfort. They developed a very nice tool called Thermal Comfort Tool. Feel free to check it out by just putting down CBE Thermal Comfort Tool. It's free and you can have access. And you can kind of tweak all those 6 primary factors of ASHRAE 55 and see if your occupants in the room still are within that ranges of comfort or not. It will give you both ASHRAE 55 and EN 15251 as like the two references of the standard. So check it out. They also have a nice tool. It's called RAT tool. It's a phase one derivable, let's say, radiant heating and cooling calculation. If we had a chance to talk to any of you guys further about radiant cooling system, I'm going to definitely mention that RAT tool. If you want, please go and check it out, CBE RAD tool. But these are some, as mentioned, rule of the thumbs that I'm going to mention. When you're thinking of your slab configuration, first of all, you need a layer of insulation where your tubing is either stapled to it, or some projects they add a mesh layer and then they just fasten the tubing to it. In this insulation layer, we always ask you guys to go and check it with the local jurisdiction for the minimum requirement. But what we normally say as a rule of thumb is R10 for a slab on grade, or we always say it should be 5 times more than whatever you have above tubing. So let's say you have almost R 1.5 above your tubing, considering the concrete and your floor finishing. We recommend having 5 times more insulation underneath, like R 7.5 at least, to make sure you are redirecting at least 80% of the heat towards the surface above, and only maybe up to 20% is get wasted as a sort of backloss. So these are very important to have that insulation. I get the question a lot working with our clients that do we need an insulation? The higher your insulation is, it means your system is working more efficiently, less waste of energy, and also fastest response of your radiant application. Another great thing to consider is the pipe elevation within the slab. I talked about it in one of the slides, that what is the minimum requirement of having that thermal mass above tubing. Like in the structural slab, we require minimum 2 inch, and in non-structural, minimum 3/4 of an inch. But there is also a maximum as well, like for your system to work more efficient. You cannot just bring the tubing down to like 15 inch if you have a very thick sort of a slab. There should be in the thicker slabs always a layer of rebar that you can tie the tubing to it and bring it up as much as possible. So if you are as close as like that 2 inch to the surface, you're making sure you're having the optimum system performance. And I would say you can bring it down to 6 inch from the surface, but going lower than 6 inch, it's not like your system is not gonna work. It's gonna work, but you first of all require higher supply temperature. Second, your system lag time and the response time would be more and considerable to compare, where you have it closer to the surface. So always consider bring it up as close as the surface and keep that 2 inch in mind. Next topic would be pipe size and spacing. So we have a rule of thumb for the different application. Like for regular residential, we normally go with 1/2 inch pipe. It's easy to work with, very flexible, 5 times OD. You can go 6 inches on center with no problem. And depending to the code, again, some part of the country, they require the first 2 rounds to be at 6 inch, and then you can go 12 inches on center. Or some people prefer to have it all throughout 6 inch to utilize this advantage of radiant system of having a very low temp system. So again, the tighter spacing you use, you will end up in a lower supply temperature. Or if you have, for example, a big warehouse, the one that Max showed as an example, that zone number 9, you will go with a relatively larger pipe size, like 3/4, because you can run longer. In this chart here, you can see the, again, typical circuit length, where, for example, we prefer to see half-inch pipe around 100 meters or 330 foot. You can bump this up when you're using a 3/4 inch pipe to 500 foot. And this can help a lot with the applications like warehouses or bigger spaces, because you can go longer loop and you save on your manifold size. That's one pricey part of the system. Again, that's our jobs as a designer to come up with the optimum solution of the pipe size and spacing, where you both make saves on the pricey part of the system, and also you have a more efficient radiant application. Other, let's say, rule of thumbs or important things to consider is the flooring material. For sure, we get that question a lot, that what sort of a flooring material you recommend. The lightest possible is, preferable. Like bare concrete would be the best thing for me as a hydronic designer, because you experience minimum resistance above your tubing. And like carpet would be the worst. It's like, putting a blanket over your baseboard and you still expect some heat from it. So we always encourage you guys to go and check the data sheet of your flooring material and pick the lightest R value, because that will help with your system response time, and also the, let's say, supply water temperature. Lightest you go on the floor, it means you're gonna have a lower water temperature, and as a result, let's say, more efficient system. I talked about indoor design set point. When it comes to radiant application, always think about 68 to 72 degrees. I was talking to some of our clients here in California. They were like, we never go above 68. People feel comfortable having 68 degrees in this region. But for some of my clients in Canada, like, I don't know, in North Alberta, or in, like, for example, Saskatchewan or Winnipeg, for example, they are more comfortable to set it at 72 degrees. But again, 68 to 72 is enough. If you want to cook everyone in the home, feel free, crank your thermostat to 75 degrees. The floor temperature range, again, we have guidelines for it. And the photo in the lower right, you can see it has a very direct impact on your radiant system capacity. Say if you cap your floor surface temperature at 85, the max you would be expecting from your radiant system is 34 BTUs per hour a square foot. Or in some applications, if you can bump this up to, for example, 91 or 95, you can even see 54 BTUs per hour a square foot out of your radiant system. So what are the main barriers here? First of all, ASHRAE standard, or CSA for my Canadian friends. ASHRAE, there is a big red flag if you are passing 84 or 85. So they don't want to see anything above 85. But CSA is more flexible. It's okay up to 90 degrees. Like, for example, in the bathroom, since you are limited in the floor space, and it's always feels good if you come out of the shower and you're experiencing a little bit of a warmer floor surface. They allow for, higher temperature, but keep that in mind. That will have a, direct impact on your radiant system capacity and output. Another thing here is the floor manufacturer, let's say, companies. Like if you are using engineering hardwood, some of those companies, they don't want to see temperatures above 83 maybe, and it comes again in their data sheet. Please double check. And that's why we always recommend installing these radiant systems with a floor sensor, so you can have a good control on your floor temperature, both on the comfort side and the fact that you don't want to harm your floor finishing. Supply temperature, there is a big red flag for radiant industry, especially if the pipe is installed within concrete, which is 140 degrees. Uh, and again, the whole topic of radiant is having a low temp system. So considering these new building envelopes, how tight the buildings are, even in Canada, we don't see, in the colder regions, we don't see buildings needing, more than 120 degrees supply water temperature. So if we end up as a designer with numbers like close to 140, it's always a red flag that we want to see the owner, we want to talk to the mechanical engineer, and or revisit our calculation to see how we can bring this temperature down, because we want to have a more, let's say, energy efficient system which works between 90 degrees to 120, 110 degrees. That's why this system is a great match for your geothermal application. That's why this system would be a great match for your district heating energy. I'm from North Vancouver, and there are many projects which are connected to Lonsdale Energy Corporation, that they have a supply energy cap which is 110 degrees, and again a return water temperature limitation as well. So everything is calculated that way, that the systems are working optimum and in the most efficient way. That's why if your system inside the building needs to match that by having a good performance around, as I said, 90 degrees to 110 or 120 degrees supply water temperature. Last but not least is the delta T. Max mentioned at some point of his slides that ending up in some GPMs like zero point 0.2 doesn't make sense for the balancing, for the pump sizing. That's where we tweak the delta T. Normally, as I explained, it's 20 degrees Fahrenheit for the, let's say, best practice. But if I end up with very lower ranges of, let's say, GPM, I may bring that delta T to 10, sometimes to 15, to make sure you get a more reasonable GPM per loop and as overall in the system, so you can find a more reasonable pumping system for that. You may be able to bump this up to 25 degrees, again, based on your GPM, because you want to end up in a reasonable GPM ranges. But again, keep in mind, you don't want to experience a big delta T, because you don't want to like thermally shock the slab. In some cases, if you go above, for example, 30 degrees Fahrenheit, the thermal fluctuation in the slab is that much that you may see some cracks. So always keep that in mind. I think I covered all the major topics when it comes to radiant design, the best practice, and the questions that I get. But I'm gonna open it up at this point for any questions that you guys have. I think we are doing good on the time, Max, right? Or you have any comment, Max? Feel free.
Yeah,
We'll be more than happy to address.
I've got a bunch of questions here, and one of the things that just came in as far as the floor temperatures, if you want to go back one slide,
Sure.
um, the at some point your feet are going to sweat. So if you if you get that much warmer, know that that's the part of the reason. If you get above the temperature of your skin, you start to feel like you're on a warm sidewalk or something outside in the sun. And that's part of the discomfort. And that always makes me laugh with ashrays. You can't quite say what comfort is, but you can establish boundaries of what discomfort might likely be, or whatever kind of the official
Definitely.
book answer
Mhm.
is there. But those are good limits. And like Saeed said, that I think that Canada, the CSA, has some really good caveats for that, as far as like a pool deck or something like that. They're like, hey, you might be able to
Mm,
go a little bit warmer here, because that is kind of the expectation, that you would want a warmer temperature just getting out of a swimming pool or something like that. And then we have a bunch of these questions. I'm wondering, Said, if you want to go back to the slide that had our basic office and warehouse, and this might be kind of a good way to walk
this one?
through a couple. Yeah, right there. So let's say one of the questions is about slab insulation. So one of the things that I know is important, can you model with LoopCAD or a design software if somebody said, well, I don't know if we need side insulation on the side of the slab here. What's
Mm.
kind of the difference that could make to have some, insulation on the side of a slab versus just on the bottom?
Question. For sure, you can model it with LoopCAD. And if you are not forcing the BTU, it means if you are letting LoopCAD to do the heat loss calculation, the item that it consider is always, insulation. either in the wall or in the slab or in the edges, and that will have a impact on your, let's say, back losses or directional losses. And it will, you can see if you, for example, tweak that number and apply different R values, you can see the impact on your GPM. So if there is no R value on the side of the slab or even at the bottom, you will end up in a higher GPM to compensate for that. But if you go like, with a good R values for those sides that I mentioned, you will end up in a lower GPM and a reasonable, let's say, head losses.
And you had a good question or you had a good answer for wood. So if you wanted to do hardwood floors somewhere, sometimes I think that the underlying part of it is, that you could warp the floors, or that you might start to smell the glue of the floors if you had 160 degrees
Yeah,
water going through them. But maybe in this example, let's say, go back to the, oh, sorry, I asked you a
well,
question
it's
there.
okay. Yeah, just wanted to go through the, different R values of the floor, but
Yeah.
you brought up a very good topic. I would say like hardwood floor finishing manufacturers are very sensitive on that. And some of them, they already have some indicators. You probably know this better than me, that they put it underneath the wood. And then if some warranty claims come up, they come and rip the wood out and then check that indicator. It changes in the color. So for example, if that was originally blue and now turned to red, it can tell floor was, exposed to higher temperatures than like 85 or something, then your warranty would be void. So that's why I emphasize on having a floor surface temperature sensor, and you can hook it up to your thermostat to set as a higher limit of floor temperature. If you guys having a engineering wood or any sort of the floor finishing that you want to keep it safe, you can define that higher let's say temperature limit on your floor and be safe always.
And that was a question we had too, is like, how do you control these things? And your answer there about having, you want to know the temperature, the air temperature of the space, but also the temperature of the slab. And
Mhm.
do you want to cover where to put the floor sensor? That's always a really frequent question. Do you want to put that like right next to the pipe, or where would you put a floor sensor if you had, 12-inch on
Yeah.
center spacing as an example?
That's a great, again, question, Max. First of all, we always recommend to have this floor sensor inside of a conduit, like a piece of PEX pipe even, because you can, change it in future if something happens. Then always in between of the supply and return tubing, like if you're having a 12-inch, try to be at that very center line so it has a more accurate reading. That's the whole idea. Don't be so close to the exterior unless you wanna, address the worst case scenario. But you're right, like picking a good spot for, let's say, floor sensor is very important. Again, most of the floor sensors in the market, they come with like a certain amount of, let's say, wiring, 6 to, I don't know, 10 foot. You can always add to this, but keep in mind, going with the longer, let's say, wires, you're bringing your accuracy down, the reading accuracy. So always keep that optimum distance from your, let's say, mm, thermostat as well. Yeah.
And maybe that's like, maybe we can kind of talk about this in this building. So let's say we've got all these different types of rooms. Was
Mhm.
that one slide before that showed kind of what they were? Those, yeah.
These.
So let's say that zone 9, that big warehouse, maybe as you mentioned, you go with 3/4 inch pipe and you've got wider spacing. That's not going to react very quickly. And that's okay.
Mhm.
Like you wouldn't turn on that slab at 6 in the morning and turn it off at 5 p.m. You're going to kind of put that in cruise control, and you probably want that warehouse to be warm throughout the heating season. But that might be
Mhm.
completely different from circuit number 8, that yoga room. So what would you do if you wanted to do radiant in that zone still, but you wanted a little bit faster reaction time? So maybe you could
Mhm.
put like a little bit of a schedule, not 10 degrees Fahrenheit or anything like that, but warm it up
Yeah.
for a specific time in the day. What would you use as a radiant installation method for something that you wanted a quicker response time?
That's a very good question. Again, for the high thermal mass buildings, you don't have much of a option. Again, if you have 2 inch or 3 inch of, let's say, concrete coverage, you have to allow, if it's doing, it's a startup, for example. Uh, but we always recommend to keep it at idle mode and using, for example, programmable thermostats. If you are expecting the occupants to, for example, come at 8, you always come pre-program it into your thermostat so your system kicks off from idle mode to whatever it is designed for an hour earlier, just to be safe, for the smaller rooms like room zone number 8. But again, if you are dealing with some of those panels that I showed, because those are very fast response, that's a different scenario. You can technically expect a maximum 10 minutes, let's say, lag of a system response in changes of the floor surface temperature. So based on the occupancy and the how thick is the, let's say, thermal mass, we can always plan, but a good control strategy is the key.
And you had mentioned too that the different pipe spacing too is one way that you can work with that too. So you could do tighter spacing and you'd have a little bit quicker response time. Or even in that, like office number one, that as you
Hmm.
mentioned, you might have a like 6 inch spacing on the perimeter on the like the west and the north if those were directional. And then on in office two and three, maybe you don't even need to do that, but that can help to just put a little bit more pipe into the space instead of having different temperatures or having to get crazy with balancing. You can kind of balance with the amount of pipe and the amount of spacing and even the depth in the floor. So that was another question that I know came up sometimes is let's say
Mm,
out in the warehouse, let's say this is an aircraft hangar, which is always like a perfect example of a good use case for radiant heating. Because if you open an entire wall to bring a 747 into that, and you're just using hot air that you're blowing into this space, it all leaves. And if you have a nice warm slab, then first of all, the mechanics love that if they're working out on the floor, but then it's going to just recover a little bit better because you have that whole nice bed of sand on a beach basically that's as soon as you close the door you're going to feel warmer quicker than if you had to reheat the entire volume of air with hot air from the top down. So let's say out in that warehouse, one question that came up, let's say you put 3/4 inch pecs in there, but you're going to park an airplane on the top of it. Is that a structural issue for the slab? Are you going to crush that slab, Saeed, or are you in good shape?
that's a very good question. We get that question in like the mining equipment, let's say buildings as well, because they bring those big, let's say, what do you call it, monster trucks. Um, but first of all, we always want to check this with the structural engineer to make sure the, let's say, concrete compound can take that much of a stress and load. On our side, on the tubing, when I set that number of 2 inch, we are confident. So the tubing is pretty robust. If the let's say structural is confident with their 2 inch concrete coverage, that won't change it. But in some places that there is a risk. Again, you can always go lower elevation. As I said, the optimum range would be 2 inch to 6 inch. If you go lower than that, we always again uh, encourage people to have a let's say, or either as you mentioned, going tighter spacing to have more pipe, or coming up with a better control strategy to kind of plan this in advance. Yeah,
Yeah, and I think that's it's hard to compress water too. So if that pipe is filled with water, it's not going to crush like it's a balloon filled with air or something in the concrete. So you should be in good shape there. I remember that the times that that came up and they were looking at like, well, wait a second, what if there is the monster truck like you said on top of it? It's hard to compress water.
that's true.
So you're going
Yeah.
to be in good shape there. Let's see. So then another so the controls as far as what you're looking for, one question we had is what if you have a couple zones in a basement and you've got like a big basement and then a couple bedrooms there. So when do you need a new thermostat? Is that one zone or three zones, or how would you figure that out as far as a control strategy goes?
That's a very interesting question because that comes to the end user and how, for example, the occupants prefer to see it. To me, I always say to our colleagues when we're designing any enclosed areas, any place that has a door, I want to have it on a separate thermostat for a better comfort, let's say, point of view. Like even bathrooms, I want it to be on their own zone. So I would say if you have, for example, a two-bedroom apartment, at least I go with three zones there. I would consider the dining room and the bathroom on one zone, and each of the bedrooms on a separate room zone. But we get lots of designs that even in a three-bedroom apartment, they want everything to be on one single thermostat. Because again, in their book, maybe they're saving a little bit of a, let's say, initial cost. But to me, the comfort plays a very important role. That's where you, in many buildings, you can see one bedroom, it's like sweating hot. The other bedroom, the occupants, open the window and they're enjoying the breeze. So if you have a good control strategy, if you consider these multiple zones, you're bringing your, let's say, energy cost down. And again, we talked about this since our manifolds have the capacity of being controlled like on each loop individually. You can have as many as many thermostats per building as you want, and connect it to one of those valve actuators on each loop, and make sure those zones are let's say talking to each other, and you get proper temperature in each area.
Yeah, and I think that if this building we're looking at here were a residential example, the control
Mhm.
strategy with the floor sensor and a radiant thermostat that has a maximum floor temperature, you can also set like a minimum floor temperature. So if zone six there was a bathroom, that's on the inside of the building with a bunch of warm zones around it. So
Exactly.
that thermostat might not call for heat very frequently, but then everybody's like, hey, why is the bathroom floor cold? That was kind of a
Mhm.
requirement that I had for this house or whatever. You can actually set that as a minimum temperature too, so it's always going to keep the floor warm enough. You don't want to do that in all of the zones, but that might be important in a bathroom specifically that still works with that control strategy with the radiant thermostat and
Great
the.
point you brought up, Max. I've had clients that they said, okay, no matter it's summer or winter, for example, my grandma enjoys the warmer floor. So even in the like the shoulder seasons or some part of summer, they supply the, let's say, very lower, warmer water temperature to make sure they get a bit of a temperature, because they were sensitive to a cold surface. So setting up a lower limit is always an good option too.
And then I've got something that we could try if you're up for it, Saeed, because you talked about the radiant the thermal comfort tool, the CBE calculator. If I switched over and took the screen, would you be able to kind of walk me through some of the parameter changes to make there? That
Sure.
was related to a couple questions, and I've got it pulled up here. So I'm just going to make myself the presenter and then show that screen for people that
Okay.
want to stay on. We're just past the top of the hour, but I think this ties together a lot of what you've
Oh yeah,
said and is
definitely.
helpful for the design. Okay.
So are you sharing already?
Yeah, I think
Okay.
that, so I've got that up. It looks like it's sharing now. So this is just a live view of the CBE thermal comfort tool. But a couple things that you can do with this tool specific to Radiant is you can change this to psychometric air temperature. And then what you also unclick this operative temperature. Am I doing that right? So now the cool thing is you can change the air temperature and the mean radiant temperature here. So if you had a mean radiant temperature that's warmer because you're warming the floors, do you need to have a really hot air temperature anymore on your thermostat, Saeed? What kind of is the effect there? Or I can plug in different variables if you want to.
Yeah, again, that depends if, for example, somebody is studying or they're running on a treadmill, again, what clothing they're wearing and everything. But as you mentioned, if we are focusing on mean radiant temperature, you can definitely bring that air temperature down to the ranges that I mentioned. And I think we would be still in the comfort range.
And I'll just kind of play with some of these parameters and you can see how I'm
Yeah.
moving the box around there. So then what if I went with 72? I'm going the wrong direction there. But if the mean radiant temperature, and I changed it to, reclining, we could do somebody who's burning a few more BTUs typing and
Exactly,
see where that
exactly.
moves it. And that's where, the exercise part, that was one of them. that's really going to change it. So dancing, you're going to be,
Yes.
in a whole different scenario there, which I think this is a good way to model all these things because you can see
Hmm.
how you can bring the air temperature down if you've got a warmer mean radiant temperature. And play with these different factors. Again, a lot of the calculations that were made for clothing level back in the earlier ASHRAE days, we're assuming it was just like a man wearing a suit was at work. If you were like in a boardroom, you were going to be a man wearing a suit, and that's very much not the case anymore. So that's something that you can model that like, okay, the average clothing is going to be a little bit different variable here than it was in that scenario that everybody was assumed to be and higher metabolic rate and wearing a suit or
Exactly.
something like that. So that's just a very cool tool that I like to play around with, and also gives you more confidence as kind of spills into the other conversation we mentioned at the very beginning with radiant cooling. This is how you figure out that like, oh, okay, if we can reduce the temperature, the mean radiant temperature in this room, we really don't need to get that air temperature so cold. So the temperature that you see on a thermostat, there are some cases where people that are new to radiant, it's almost like cover that up with painter's tape and adjust the temperature up and down and see where you're comfortable, because you might be surprised that if you've grown up with forced air, you think you want the air temperature and heating really hot, and you just don't need it if the floor is already warm. But that lets you split the adjustments here. So that's why I really like that CBE tool. And thanks to you and the REHAU team for working on that with the group of experts over the years too. I think it's just a very valuable way to kind of see where you're going to fall out of compliance of the ASHRAE standard 55 for comfort, because then we don't win. Even if it's very energy efficient, if you're going to be too cold or hot, we're in bad shape there.
Exactly. Yeah. We're happy to be part of these tool developments. Again, anyone in the room is still, seeing this, feel free to check their radiation tool or RAD tool. It's a good tool to explore your radiant cooling options if you guys are interested. So hoping maybe sometimes in future, soon future, with my friend Max, we could do that one and we walk you through those slides as well.
I'll bring that one over so you can just kind of see this grab of the rad tool there too. So yeah, very, very useful to give the designers and installers more confidence that like, hey, this would work. This is a good way to do it. I need to know that these are the requirements. And this is what would be a deal breaker potentially. And everybody wants to know those as well. If somebody asks you, Saeed, that, hey, I want to do a restaurant in New Orleans that has an indoor outdoor space, and I want to do radiant cooling, and we want to make it cold enough that it's keeping the drinks cold. Is that like a good fit for anybody?
Oh, definitely. As a matter of fact, we had a discussion yesterday about putting this in a wine cellar. Again, you have a good flexibility when it comes to this system, and the fact that you mentioned, like for commercial businesses like that, always this system Radiant is a part of a hybrid system. If it's gonna be a radiant cooling, it works hands in hand with a DOAS or dedicated outdoor air system, and you are more flexible to kind of monitor the relative humidity of the room to make sure those condensation risks are mitigated, and also your let's say comfort type of heat transfer is always delivered to the occupants of the room.
Yeah, and that I think is important too, that we're talking about a building that has an envelope, that you're not just exposed to the great outdoors, because it's
Yeah,
not really
exactly.
so much a consideration of the local humidity levels outside in Salt Lake City versus New Orleans or something like that. You need
Mm,
a structure that you're able to control the humidity levels, but that's going to be code compliant anyway. So if it's a
definitely,
new
definitely.
construction building, you should have those controls, or it's probably not going to be up
Mm,
to what we're supposed to be doing with new construction anyway. And that really sets you up with this, ASHRAE standard 55 and 62.1 for kind of the humidity control. Essentially, those are the boundaries that are already pre-existing that set you up
yeah,
for success there. So
exactly. And again, except if it's a area with the humidity spike, like all of a sudden you get a hot humid air. Those are the risky point of the system. And as you mentioned, if you are avoiding areas like bathroom with the showers, or your building envelope is tight enough, you not dealing with great risks of condensation in your project.
Yeah. Well, I think that goes through the most frequently asked questions we got in the chat there. There are a few others that we'll respond to after the fact that look a little bit more project specific. But
Mhm.
I will stop there and thank you, Saeed, for joining us today. This was great and was
Thanks for
a
having
topic
me.
we got a lot of engagement with. So we'll look to do another maybe radiant cooling revisited topic at some point soon. We'll let you get back to your skill builders training there in uh,
Thank you.
in Reno, and we appreciate it. And talk to everybody soon. We've got Kevin Freet up next month to talk about DHW recirc troubleshooting and FAQs. So see everyone soon. Thanks.
Thanks again. Have a great day.